Good morning. My name is Detlef van Vuuren, and I'm working at PBL Netherlands Environmental Assessment Agency, where I'm leading the Image Integrated Assessment team. Clearly, the world is currently in a health crisis, but the title of this conference originally referred to the global environmental crisis that we're in, as is well illustrated by three recent assessment reports from the IPCC in 2018, indicating that emissions of greenhouse gas continues to increase, the FAO indicating in 2019 that 820 million people still suffer from hunger, and the IPBES report indicating that the loss of global biodiversity is a threat to human well-being. It's also well illustrated by the planetary boundary figure that indicates for a set of global environmental problems in green, if the situation would be safe, but in yellow and red, the risks situation for several environmental problems because the planetary boundaries are transgressed, which is the case, for instance, for climate change, biogeochemical flows, and biodiversity. But we should not only be looking at the current situation, but also into the future. And there are two different figures emerges. One, on the one hand, the situation could continue as it is today. And at the same time, we have also promised as humanity a set of goals. For instance, the Paris Agreement, where we have promised to stay well below 2 degrees and preferably even below 1.5 degrees. And the Sustainable Development Goals, where we have to promise to eradicate hunger, eradicate poverty, and to protect the global environment. So a critical question is, what is needed to change course, or more broadly, what could happen in the future? That is a very difficult question, of course. If you want to answer that in the context of sustainable development, one would need to know things like population growth, socioeconomic development, changes in technologies, but also political changes, like, for instance, the outcome of the elections in the US this year in 2020. But one also needs to know the demand for different resources. But not only that, one would need to know that for different scales, as scales are connected. One needs to know that for different time periods. For instance, decisions today might have a big influence into the future. One needs to know the interactions. For instance, decisions for climate change have impact for biodiversity, the use of biofuels. And one needs to capture the uncertainties. For that, we have an instrument of model-based scenarios. These model-based scenarios are not meant as predictions, but borrowing and compare an analogy from Ottmar Edenhofer, they're much more comparable to map making, where we have a set of different goals, and scenarios can be used to explore the landscape and explore different routes and find out what we might encounter on these different routes. Just to look to that a little bit in more detail, the models that we would need for environmental problems in the context of sustainability are models that describe the human system in the relation with Earth systems. We call these models integrated assessment models. These models can reasonably well describe physical entities, the environment, but also infrastructure. To some degree, they can also describe the rules of human behavior by economics, but they obviously have a hard time describing many of the social factors, beliefs, the cultures, and things like that. And so what we do is to combine the outcomes of models with different stories of the future. And together, we can use this to describe possible scenarios of the future and indicate what is possible and what is very unlikely. And this approach has been very successful to support climate policy. For instance, the AR5 of IPCC played a major role in supporting the Paris Agreement. But for many of the SDGs, scenarios hardly exist, and there is a clear need for scenarios that cover multiple SDGs, also to identify the synergies and trade-offs between different strategies to meet these SDGs. I want to illustrate this again a little bit further by looking specifically to climate change. And if you want to look at climate change, you obviously have to describe the full chain of climate change, starting from drivers, population, and economy, up to energy use, emissions, concentrations, climate change itself, and the impacts. Now, if you look at this from the endpoint, impacts, there are actually two major things that determine the impact. On the one hand, it's the climate change, but at the same time, it's also the socioeconomic conditions. If you compare, for instance, the impact of sea level rise on the Netherlands and Bangladesh, it's a totally different situation. One country with the same level of sea level rise might be able to cope with it, given its governance structure, its level of development. But for the other country, it might be a much worse situation. And so we decided to structure the scenarios around these two factors, socioeconomic development and climate. That gave us a matrix. And the matrix is on the one axis, it has the climate situation, going from 8.5 watts per square meter additional forcing, comparable to around 4 degrees warming by the end of the century, to 2.6 watts per square meter, which is comparable to the Paris Agreement, about 2 degrees warming, or well below 2 degrees warming by the end of the century. That's the one axis. The other axis, we wanted to say something about possible socioeconomic pathways. And for that, we obviously had to think of different ways that the Earth could develop. And for climate change scenarios, they have to speak to climate policy. And there are two major ways that climate policy might emerge. One is mitigation, and the second one is adaptation. And so we thought it would be helpful if our scenarios might actually address these two response options. And so we wanted to have scenarios where it would be relatively easy to adapt and relatively easy to mitigate, but we also wanted scenarios where it would be really hard to adapt and hard to mitigate. Now, in the first situation, if population growth is relatively low, if there is a relatively wealthy society, if technology develops rapid, if there is good governance, then it's relatively easy to adapt and relatively easy to mitigate. In the opposite situation, where there is high population growth, people are poor, people are actually competing with each other, in that situation, it might be really hard to adapt and hard to mitigate. And you can also think of situations where it's relatively easy to adapt, but very difficult to mitigate. For instance, if we would have a very strong development in the direction of fossil fuels. We sat down with about 60 people in around 2015 and started to translate these 5 possible worlds into storylines. And we, along the lines that I just indicated, for SSP1, we described the world, which could be described as green growth, with a lot of global cooperation, already some dietary shifts, rapid technology development. And on the opposite axis, SSP3 was a world where we described regional rivalry, competition between the regions, population growth would be relatively fast, maybe you could say the clash of civilizations. And so we did the same for the other 3 stories. And we said that we did this in a couple of days, and after that we continued to write these stories for about a year. And then we went to the models, and we asked the modelers to further develop these stories by computer models. And for instance, we did this for population and income, but we also did this for energy scenarios using the integrated assessment models. And here you see the outcomes for energy, for the global energy system, for these 5 different storylines. And they're all still without climate policy. And you see very different futures. On the one hand, SSP1 with a relatively low energy development pathway. On the other hand, SSP3 and SSP5 with a relatively high energy pathway dominated by, among others, fossil fuels. In the case of SSP3, for instance, a lot of coal as the regional situation with relatively little trade forces some regions to use the domestic resource, which is coal. But if you look at all the scenarios together, you see that actually in all scenarios there's a further increase of global energy use, and fossil fuels, at least to the mid-century, continues to be important. and as a result also increasing greenhouse gas emissions. So again, we use our models to translate these energy pathways into pathways for CO2 emissions, as shown here. And you see indeed that compared to today, the scenarios either assume more or less a stabilization or a major increase. And we can then also use climate models to translate this into global warming scenarios. And the outcome is that in the most optimistic scenario without climate policy, SSP1, the increase is about 3 degrees compared to pre-industrial. And in the most pessimistic case, SSP5, the increase is above 4, almost 5 degrees. And on top of that, we have the uncertainty of the climate models. Now, this situation would lead to quite some climate impacts, much worse than they are today. But the big question is, can we change course? And to stay well below 2 degrees, or even below 1.5 degrees, it is possible to estimate how much CO2 emissions we can still emit. And for 2 degrees, this is about 1,000 gigatons of CO2. For 1.5 degrees, this is about 400 gigatons of CO2. And that's not a lot, given this, the fact that current emissions, at least last year, are 42 gigatons of CO2. So for 1.5 degrees, the budget is about 10 times the current emissions. So in terms of going straight down, it actually means reducing emissions in about 20 years to 0. It translates in emission pathways like this. And again, we have used the models to design corridors consistent with these targets. For 2 degrees, it more or less means going to 0 slightly after the middle of the century, and then possibly some negative emissions to compensate for the overshoot in the first half of the century. For 1.5 degrees, it's even going to 0 around mid-century, and again, possibly negative emissions. If you want to avoid these negative emissions, the emission reduction has to be even faster. But you see already these scenarios are a large break with the current trend. We can also use the models then to see how these energy systems would look like compared to the baselines. And the good news is that we can design energy systems that are consistent with these pathways. Yeah? So technology-wise and economically, these pathways are feasible, and they will mean a large shift compared to the energy systems that I've described earlier. Just to summarize across all the scenarios, what it actually means is that above all, there needs to be a focus on energy efficiency. By reducing the total energy demand, we make the problem much smaller. We also found out that in the power sector, it's relatively easy to go to 0 emissions. And so that would be the first step, invest a lot into renewable electricity. The fact that it's relatively easy in the power system to go to 0 also means that you want to electrify where possible. Possibly, we also need to develop the negative emission technology. In fact, for 1.5 degree, it actually is almost impossible to do without negative emissions. And so we might want to start developing these technologies already now. We also need to decarbonize the much more difficult sectors, which are parts of industry and parts of transport, like aviation. And there we need to think of other options like biofuels, CCS, hydrogen, or solar fuels. It's also necessary to mitigate the non-CO2 emissions, which is relatively hard for some sources of methane emissions. We can reduce emissions quite a bit, but reducing them more than about half seems almost impossible as long as we have a high meat consumption. We also we need afforestation. And finally, and maybe it's not finally, but it should be one of the first options, it's important also to think of lifestyle change. And this is, for instance, related to the remark I just made about non-CO2 emissions. if it's almost technically impossible to reduce the methane emissions further with, in combination with high meat consumption, reducing meat consumption actually means that it is possible to reduce the methane emissions. So far in my story, I've been talking about the connections between human activities in terms of greenhouse gas emissions, indicated by the gray arrows in this graph, and about the energy relationships, indicated by the red arrows. But there are much more connections between these systems. They're also connected in terms of land use, in terms of biomass flows, and in terms of water flows. And so if we change systems because of climate change reasons, we also have impacts on land use, on water consumption. And here again, scenarios can help us to understand some of these consequences. So maybe we can look at the planetary boundaries again. And here I've shown the development of the planetary boundaries between 1970 and 2015, according to the IWIT model. And we already saw that for several of the planetary boundaries in 2015, they were transgressed. If we then use the SSP2 scenario and look into the future, you can see that the situation would continue to become worse for many of these planetary boundaries, with the exception maybe of air pollution, where we actually see some improvement. Now we can also try to, again, ask the question, is it possible to change this? And we did some calculations where we introduced climate policy. We also introduced diet change, not to vegetarian diets, but simply changing diets back to a healthy diet. That would mean a reduction of meat consumption. We also assumed a reduction of food waste, and we assumed higher yields. And we already could show that we could significantly improve the situation from the purple SSP2 line back to the blue SSP2 450 line. That's the climate mitigation scenario. We have done this for planetary boundaries, and we're still exploring scenarios here, because obviously you might want to think of other policies that you want to integrate here as well, for instance, water efficiency policies, or specific policies to address the nutrient flows. But you might also want to go a little bit further and think specifically how to combine different sustainable development goals. Now, we are currently still working on this, and partly in cooperation with other integrated assessment models as part of a project called the World in 2050, where we take the SDGs as a first step and then think of scenarios that could continue to go into a direction of sustainable development. This is actually what I wanted to share with you today. Thank you for your attention, and I would like to also go into your questions. Thank you very much.
Thank you, Detlef, for that very interesting and somewhat quite alarming presentation. So if we have you back on the line here again now. There you are. I hope you're on. I would like to ask you some questions, because there you are. Hello. So one thing that struck me is that you're dealing with extremely complex problems and variables, etc. And scientists are often criticized for using the term of uncertainties. Normal people tend to have trouble understanding what this uncertainty is all about. Do you think that using those models that you've used and you know, sketching out these scenarios, is that a way of reducing the uncertainties and also making this picture easier to see, although it's still quite complex?
Yeah, I do think so. And I like this analogy with this map making, and to try and understand the landscape a bit better. Well, still, there's a lot of uncertainty. And so if we go all 10 years back and we were looking into climate change, I think none of us would have expected that renewable energy or also storage of electric electricity would develop in a way that it has done, and therefore potentially making the response to climate change a bit easier. So taking it into account uncertainty is important, but at the same time, I think it is useful to take the knowledge as we have and then start to think a bit into the future and to understand what is needed. And so, for instance, understanding how fast emissions need to be decreasing to meet the Paris goal, how fast we have to scale up renewables, for instance, what would be the consequences of a more renewable pathway or a pathway with more CCS. I think those are useful explorations.
But at the same time, we're talking about an extreme speed which is needed in order to get where we want to. And there was a lot of yellow and red in those charts of yours. And even though you were showing that, yes, things can be done and we can moderate the pathways a bit, there's still a gap between what we know and what we actually do. And we're going to discuss that later on as well. But if you're willing to share some of your perspectives on that already, please feel free to do so.
Yeah, so for climate researchers, this is also obviously quite frustrating. So with IPCC, there has been this warnings that we really need to change course now to make an effective response to climate change. That has been a message that has been sent out maybe already for 15 years or so. And it was true. We have made it much more difficult now to respond than if we would have responded 15 years ago. But at the same time, with the scenarios we are showing, that it is possible at least to meet the well below 2 degree target still. The 1.5 degree target is also still possible, but that becomes really challenging. And certainly given the new information on climate sensitivity, so models are now indicating that maybe the climate is even more sensitive than we thought before.
Yeah. So you still, despite all that, you still think 1.5 is feasible, because one of the charts that you were showing told us that even the most optimistic pathway was ending up at around 3 degrees. But that, of course, that was without stringent climate policy. But to me, it's completely realistic.
Now, so I first of all, I think it's really doable, and it would be really, so stupid if we wouldn't go this meet the well below 2 degree target. In principle, technology-wise, and also in terms of the changes in behavior that are necessary for that, there is something that we, as humanity, could achieve. Whether we get it done in terms of the organization of this, let's see.
Ik heb Chief de Winter
Sorry.
niet tussen je muziek kunnen vinden.
Speaking of technology. Well, Detlef, I would like to ask a question, a very popular question from Slido, actually, and we're going to touch upon it later on in the discussion as well. But the question is short and simple. Do you think COVID-19, so the current corona crisis, will change the scenarios?
Yeah, and I think it's a very good question. If we just go back to the financial crisis of 2009, and then you would see that didn't really change the course of what happened after that. So we had a drop in emission, but then after that, actually more or less things continued as before, and so this was a temporary event that didn't change much of the long-term outlook. What is happening now? We still have to see what remains, and so there's much more lifestyle change, of course, now. And are people going to keep some of those changes or not? With respect to the recovery packages, are we going to invest them in a green way or not? And also, how long will this last? In principle, the drop in CO2 emissions in this single year is interesting, but it doesn't really change too much of the dynamics in meeting the 2 degree or the 1.5 degree target. But the key question is how much of this is going to be structural and how much is temporal. And I do think especially with the green recovery packages, we could make a difference.
And I think we're going to repeat that question later on in the discussion as well, because the key word that you were just saying is structural change. Seeing a drop in the emissions is expected, but is it going to last, and how are we going to make it last, and what kind of changes do we need to get there? So another thing that I would like to convey from the audience side, which is another popular question, because you had one pathway which had CCS in it, and there's a question about this. Is CCS unnecessarily justifying the existence of fossil fuels in our energy systems for upcoming decades? Can we forget about it and yet achieve the goals?
Yeah, so I think it's an open question, and we should be researching that further. I think if we go back 10 years ago, and IPCC also published that maybe even slightly longer ago, a special report on CCS. At that time, the outlook with renewables was certainly not as promising as it is now, and so at that time it was quite clear that CCS would be a logical part of the solution. Since then, renewables, solar and wind, have developed faster than we thought. There's also more outlook on storage. Maybe electricity can play a much larger role than we thought in many sectors. So let's see. At the moment, it's still challenging to see how we can go to a 100% renewable system in power. So there needs to be some other sources there as well, and there fossil CCS could be one of the ways to stabilize those systems. There are still sectors where we find it hard to see how they can be completely electrified for high heat sources in some of the industries, for instance, and there so CCS could also play a role. But the story in the very short term is that renewables are so promising that at the very short term it makes a lot of sense to mostly invest in efficiency in renewables. Then we can see how this further develops, and whether how much CCS would still play a role.
Just a final question, because there are lots of questions popping in, and that's wonderful, dear audience, and I want to keep some of them for the discussion later on as well. But I noticed that you were talking about energy efficiency, and that was actually the first point on one of your slides. And I often get the feeling that energy efficiency is not, it's not that popular, it's not sexy enough in a way. What makes you think that energy efficiency is going to be an important tool?
Yeah, so we run scenarios where we're very pessimistic on energy efficiency, and then it's really hard to meet any of the targets, because then the problem becomes so large that you easily overrun the potentials for different renewable sources. The role, for instance, of bioenergy and land implications becomes really large, and so from the scenario analysis we see that efficiency plays an important role. You see it also in bottom-up analysis, technology-oriented analysis, that efficiency in principle is often a very cost-effective response. In implementing efficiency measures, we have not been as successful in most countries as would be suggested from the technology analysis. So with efficiency more than the supply side options, the question is how do we get the things that are attractive implemented? But by itself, it is a very promising solution.